Hi all, let's start our new lesson, new model with the new model. It's called Karna Maps and Queen McCluskey method. It's a module two that we are starting it today. So let's start with the directly and let's start directly with the basic gate. So basic gate, as you know, what is gate? A logic gate is a digital circuit which will be having one or more input voltages. So one voltage normally with one voltage we will be calling it as a NOT gate, which has a as of now it's having only one input, and other gates will be having a minimum of two inputs as always. So logic gates are the basic fundamental blocks of the digital systems where in order to construct digital system we will be using the logic gates, and because why we are using is always logic gates will be giving the output voltage in terms of zeros and ones. So even and whatever the digital system that we are trying to use, even that will also be in the format of zeros and ones. So that's a basic reason that we are trying to use. By connecting the different gates in different ways, we can build a circuits and perform some arithmetic and basic other functions associated with the human brain, like as we do some of the addition, multiplication, subtraction operations, and some of the other functionalities. Even we can do some multiplexing and demultiplexing. It can also be done using this one. So, and basically we are having a three basic gates. They are NOT, OR, and NAND, and we are also having some of the other gates. Gates are XOR, XNOR, NOR, NAND. So even and NOR and NAND gates are called as an universal gate. The reason is using those gates, so other type of gates can be constructed. That's the reason. So, and the interconnection of gates to perform a variety of logical operations is called as a logic design, and the representation of these, like input versus output against the input, will be done in a one table called as a truth table. So, and this truth table will be having all the possible combinations of the input and corresponding output. Let's directly move into the basic gates. The first let's start with the NOT gate. So NOT gate 7 NOT gate IC is a 7404, and it's at 14 pin IC, and it will be having as I said earlier, so it will be having only one input, and its output will be always inverse of the input. That means if we give a 0 as an input, 1 will be the output, and 1 if we giving a 1 as an input, and 0 will be the output. So here you can see it's a wave diagram of a not gate. And let's move into the AND gate. AND gate, it will be having a two inputs, and will be always giving a one output. So as the name itself suggests, and is nothing but multiplication operation. That means whenever the both the inputs are high, and then only the output will be high. So here this is the diagram representation of AND gate. So AB will be the input and Y output. So if we take if we put a truth table here, you can see the output Y is always high. Y is high when both A and B inputs are high. So this will be the only condition where AND gate will be having the output as an I. Even if the same thing applies to three input gate AND gate also. Here you can see the output is only high when all the inputs are high. That means to get output as high, you should always have an input as an high. So the IC number for 74 AND gate will be 7408. Here you can see. So even it's a 14 pin IC. So here you can see whenever the both are 00 in inputs are 00. So low output, pin 3 is at the output, so it's low. So 01 is also low, 10 is also low, and when both 1 1 are there, so output will be high. So this one you need to remember as an for the functionality of an AND gate. So, and let's start with the OR gate. OR gate, what we can say is simple. In simple terms, we will say it's a addition functionality. So it will be having a two input. This is a symbol. This is the pictorial symbol of a OR gate. So here you can see it. Whenever both the inputs are false, that means whenever both the inputs are 0 0, that time output will be 0. Other than that, the output will be always high. Here you can see it. So 0 1 output will be 1, because when any of the one input is high, output will be high always for the OR. Here you can see in the truth table. Here you can see it's easy to understand it very easily. And this is for the two input OR gate, and this will be for the three input OR gate. So here you can see. So in this condition, for the suppose if we are trying to get a suppose if we are trying to apply write a truth table for the OR gate, always the output will be high when you have at least one input is high, and the output will be low only when only all the inputs are low. So here you can see 7432 is the IC for the OR gate, and this is an our output wave diagram 0 0 0. So 0 1 it's 1 1 1 0 it is 1 1 1 it is 1, and the same goes on. So the NOR gate, as I said, NOR gate is a universal gate. So NOR gate is nothing but OR gate plus NOT gate. So OR gate plus NOT gate, and the output will be, first let's try to understand this symbol. So this is an output, this is an OR gate, and this is NOT gate. So this will function as like as same as that of OR gate. So what we are trying to do, output of that OR gate we are giving as an input to NOT gate. NOT gate, what it does, so it will always reverses the what is the input is coming, right? So in that condition, the output will be reverse of OR gate. That means OR gate is there and we are trying to reverse the output of it. Here you can see it in the result in the truth table. So for our OR gate, what happens, so output will be always low when when both the inputs are low, and remaining condition output will be always high. But in the NOR gate condition, what happens, so we are trying to invert output of this one output of NOT gate OR gate, right? So there what happens is, here you can see it, and the output is only high when both the inputs are low, and in the remaining condition output is low. So this is one thing you need to remember it. And IC for NOR gate is 7402, and yeah, like universality of NOR gate, here you can see. So what we can do is like this is the NOT gate. So just we are trying to type both the inputs of a NOR gate, and we are trying to give it, so that what happens here is like the input whatever we are trying to fit will be like, suppose if you are trying to give 0, so 0 0 will be go 0 will go, and output will be what should happen, so on both the 0 output will be 1. If you are trying to give this one as a 1, so 1 1 will go and the output will be 0, and the same applies to, so here you can see, so always the output is if you are trying to give A, and it will be an A bar, so not form of NOR. That's what we are trying to represent here, and OR from NOR. So already we know that what the NOR gate is an OR with NOT, and we have to invert it once again to get an exact AND gate results here. So this will be a OR gate representation of a NOR gate, and this is our AND gate representation for a NOR. So A bar B bar will be getting, and just we are trying to put into a one more NOR gate, so that we'll be getting at the end, so A dot B, and we need to use some of the basic rules that applies in a Boolean algebra to get it result. Sorry, it's not logic design rules, not a Boolean algebra. So and next let's move on to the next one, one more universal gate. It's called NAND gate. So this representation so as we have seen already, so NOR gate is a inversion of OR gate, and NAND gate is inversion of NAND gate. So here if you separate NAND, N with a separate, so N comma AND gate. So no, n is nothing but not gate of an AND gate. So this is the pictorial representation. Here you can see this is how we can construct a NAND gate. So NAND gate will be having, and we are trying to feed that as an input to a output of AND gate to an input of an NOT gate. So output whatever we will be getting, so it will be a inversion of the AND gate results. And as you all already know that, so AND gate output will be high when both the inputs are high, and in the remaining condition output will be always low. So in this condition what should happen? So for NAND gate it should reverse. That means whenever both the inputs are high, always output should be low, and in remaining condition output should be always, it should be set to high. So here you can see this is the pictorial representation. When both the inputs are high, so output is low, and in the remaining condition the outputs are high. So this is the NAND gate truth table, and here you can see, so AND gate is coupled with a NOT, so it will be called as a NAND gates. And this is the 7400 is the IC number for the NAND gate. So here you can see this is the pictorial representation of NAND gate. And let's move to the next topic, universality of NAND gate. Why we are calling NAND gate as an universal gate? So here you can see once more, like we were for the NAND gate as a NOT gate, we'll be taking both the inputs and we'll be giving it as an input. So here we will get a inversion functionality, and this will be our, already we know that. So in previously also, nor also we have seen that already we have this, whatever the NAND functionality is there, it's a inversion of AND functionality. For that we need to have one more inversion functionality to get a exact AND functionality. So that will be, that one will be doing it here, and this will be a OR functionality of NAND. So, and let's move on to the next topic, the exclusive OR gate. So exclusive OR gate, what happens is, so here we will come across two more gates. One is exclusive OR gate, and the other one is exclusion OR gate. Exclusive OR gate, what happens, it does is, so let's assume that you have a two inputs. So when any of the input is high, the output will be high, and if the inputs are same, that time output will be 0. Here you can see, and this is the pictorial symbol representation of exclusive OR gate. Here from this you can see it here. And in real time, suppose if you want to construct using the basic gates for an exclusive OR gate, this is how we need to have it. So we need to have a inverters at the starting, inverters at the initial stage, and we need to give inverted inputs of that into a AND gates. And so we need to take a direct input from the direct input, and we should give it for a AND gate as an input for the other AND gate. So here you can see it directly here. So input A is taken, and it has inverted, and it is given to one AND gate, and direct A is given to the other AND gate. So in the same applies to B also, and we have taken that output and we have fed it into we have given an input as into a one OR gate here. So and at the end we will get A bar by plus AB bar. It is nothing but, so our exclusive OR functionality. So here you can see, when any of the input is high, so output is high, and when both the inputs are same, the output will be 0. And this one you need to remember, A exclusive OR with B, so this A exclusive OR symbol. And so let's try to understand this one, exclusive OR gates too. So 0 0, so output will be 0. So so we will try to understand. And in simple, what we can say is, when suppose let's assume that if we have more number of inputs, that means we have seen it for only two inputs. Suppose what if happens if we have more than one input, more than two inputs, in the sense there might be a chances of having 4 inputs, 6 inputs, right? At that time, how it will behave, there will be a confusion, right? For that, how it can be handled is like, for the exclusive OR gate, in simple terms, what you can say is, when it has odd number of ones, the output will be always 1. Okay, when we have odd number of ones, at the input, odd number of highs at the input, the output will be always high. When we have even number of ones at the input, the output will be always low. Here you can see when suppose 0 0, it is nothing but 0. In the 1, and this is the 1 to 16 combination, you can see it here, and for 1 it will be single one, will be having output will be 1, 2 also will be having single one. Here you can see we are having even number of ones here, so 1 1 is nothing but an even number of ones, the output will be 0, and the same applies vice versa. And the last combination, suppose if you take it here 1 1 1 1, that means we are having 4 ones, one exclusive or with 1, so it will be a 0, and we will be having one exclusive or 0 exclusive or with 1, so it will be 1. So once again one exclusive or with 1, it will be a 0 only, so the output will be 0. Now this is how we need to remind you have to keep it in mind. In simple words, when you have even number of inputs, the output will be 0. Even number of ones at the input, so output will be 0. When you have odd number of ones at the input, our output will be always 1. So so we until now we have seen exclusive OR gates. Now we will be going across exclusive NOR gates. So it is nothing but the same, but as we have seen NAND and NOR, so here the whatever the exclusive OR gate is there, it will be an inversion of that. Here at the bubble also you can see this bubble is nothing but an inversion, right? So this is exclusive OR functionality, so output is inverted. That means here what should happen is when we have whenever any of the one when any one of the input is high, so output should be 0, and if the both inputs are same, the output should be 1. Here you can see that means odd number 1 should be for the odd numbers 1, the always result should be a 0, and even numbers the always result should be a 1. So this is the table here, this is the pictorial representation, and this is the XNOR representation here you can see it here. So thank you, and this concludes our session 1.